So welcome to the webinar. The topic is achieving net zero flexibility from EV charging. Welcoming those who are joining, still joining, some people are still joining. And we are now starting the webinar, achieving net zero flexibility from EV charging. And this is the topic for today. Next slide, please. My name is Yogendra Vasishta, and I'm based in Melbourne, Australia. With me, joining three colleagues from UK, very early morning there. Dr. David Mills, who is head of net zero transition, Timothy Butler, network capacity team lead, and Esther Dudek, senior consultant. So welcome to the presenting team also. They will be all sharing their thoughts in this webinar very soon. All right, so let me discuss the agenda items for today. First of all, I'll actually give you the introduction, the context, and what we are seeing, especially in this part of the world. And then we have got experts, Tim and Esther from UK. They will be actually giving overview of three large EV trials where EA Technology has been one of the partners, and what are the learnings and how did it happen. And then I'll be shortly talking about one or two case studies we have recently done for Australian and New Zealand DNSPs or EDVs. And at the end, we will talk about what is the next steps. And then Dr. David Mills will be chairing the session for Q&A, for question and answers at that. Next one, please. All right, so let me introduce this topic to you, that how the EV as one of the CERs is actually has potential flexibility, and how this can help networks, and this can help to achieve ultimate societal objective of net zero. Next, please. Now, like every jurisdiction, Australia is no different. It has its targets for decarbonization. Like, for example, in 2023, 40% of the generation in the NEM, the eastern state, was from renewable energy sources. This target itself is this 40% the target is to make it 82% electricity supplied from renewables by 2030. So just in, less than 5-6 years. So, and everyone, of course, is working for net zero transition by 2050. So this is a kind of, decarbonization target which Australia is pursuing, and I guess similar targets are there for New Zealand, and similar targets are there for UK. Now, I'm just giving you Australian perspective that, when that integrated system planning report comes from AEMO, and this is from 2024 report, that by the 2050, the kind of generation we will require will be almost triple than what we have now. It is just because, that electrification is happening for transport, fuel, and also the variable generation sources will require, more generation to have the, firm capacity. So in that respect, it is expected that by 2050, we will need triple generation, and the load will increase because of the electrification. However, this has to be managed cost effectively. To do that, there are various methods. One of the thing is how we can harness the power of distributed energy resources, and just wanted to let the audience know that in Australia, particularly these distributed energy resources are called consumer energy resources. Basically, those resources which are owned and which are initiated by consumers largely, like for example solar PV, electric vehicles, home batteries. So they are the consumer energy resources. So when DER and CER, please, similar sort of thing. They are distributed energy resources. Now, if you see the purple diagram here, that is the bit which is expected to come from coordinated CER. And this is where we are saying that this purple bit is as a result of using that flexibility in the solar system, in the electric vehicles and battery, in actually managing the minimum demand and maximum demand, and also time shifting the generation. So this is where EV will also contribute in this coordinated CER and storage. The next one, please. This is some stats from Australia. Although Australia is still picking up the EV penetration, unlike other jurisdictions, but Australia's 8.4% of all new cars sold were EVs in 2023. So it is increasing. It is actually gaining momentum, and there are a lot of car models now available. The below is given the charging infrastructure, how this is growing. So basically, charging infrastructure is growing to avoid any inconvenience or range anxiety. The EVs are having a big range now, and their number is growing in Australia also. I know that New Zealand actually is growing faster, and I'm sure the UK is also growing faster than this, but Australia is also catching up. This is the first national electric vehicle strategy just published in Australia. So basically, it has actually is so this shows that the EVs are growing, and there was a recognition to have the national EV strategy, and I'm sure it will be updated every year. Now, EVs can actually offer flexibility in many ways. One is that EV charging itself can be managed. It can be stopped, it can be time shifted, it can be throttled. We can charge at a less rate, and EVs as a storage can be used to supply to the grid or to the home batteries. And also they can actually do the solar soaking, we call it. So when there is excess solar and it is creating reverse power flows, EVs can be a good load too. So EV has got a lot of flexibility and can help in many ways in the managing the network, and also getting the value for the customers, and also giving value to the wholesale electricity market. So it has a lot of values in that. The next one, please. Now I'll hand over to Tim and Esther to provide you the UK EV projects overview.
Yeah, good morning. So we'll start off, just give you a brief bit of context from EA's side and how what we've decided to do and been working on over the last decade or so tied into what's happening within the UK market. So what's happened overall just since essentially from over the last 2014 through to 2023 years, the number of EVs have increased dramatically. Clearly, we've gone from 17,000 vehicles roughly to nearly 1.5 million. And like Uganda has just demonstrated over there, that uptake is increasing exponentially. It's going very, very fast, and the network is having to adapt in order to be able to manage that. The consequence of that is that electricity demand for road transport is predicted to peak 125 terawatt hours per year by the time we're into the 2040s. Current demand's only 320 for the whole country. So that there's significant increase of what's actually required, and a significant proportion of that overall energy mix is going to be diverted over through to electricity transport, purely because of that transportation and flipping from the internal combustion engine vehicles. So since 2005, Ofgem made innovation funding available for the DNOs, as we call them here, in order to provide this funding, in order for companies, DNOs and companies like EA, to start looking ahead, try and predict what are the uptakes and the changes that's going to happen as we decarbonise, and then how are those going to impact the network, in order to then identify and prepare for what problems and opportunities are going to exist, and how do the DNOs prepare to be ready to take advantage of those opportunities and to mitigate the problems. From our side, the regulator ensures that there's a significant amount of penalties, but also rewards for the DNOs. So for customer outages, time off supply, the DNOs will get fined. So as you start to increase the load going on through the network itself, there's a strong incentive for the DNOs to actually invest this innovation funding in order to ensure that their network is prepared and to increase. So, as mentioned, there's 3 projects that we're going to cover, but I'll briefly just give a context if it will jump to the sides. Right, jams now, there we go. So, brief context on what smart charging is in the context that we're using. So, smart charging from this context is using a series of control signals or individual ones, depending on the particular system, to alter the time or the rate of charge or both of electric vehicles in order to help manage that overall load on the network and protect the network. It may well be that you're shifting load at a time where the network doesn't necessarily need support at that precise moment, but you're doing it preemptively to ensure that you're protecting the network later and based on predictions and forecasting and so on. So the aim being, as the graph shows, to try and move this additional demand away from that evening peak, which is where we traditionally see. So you're aiming to shift it into the early hours of the morning, or if the individual in question can actually take charging in the middle of the day and there's capacity, then fine, we can move it to there. It's simply to protect the network overall, but with the key goal of not directly or noticeably inconveniencing the user at the other end. That's one of the main priorities within this as well. So the aim being, overall, from a network perspective, if we can delay or avoid ideally, but at least delay network reinforcement requirements, what that does is it allows the money they do have available for network reinforcement to be better spent, better targeted, and then also there is obviously monetary saving by delaying that investment in the first place. So 3 projects that we'll run through. First one's My Electric Avenue, so that started in 2012 and then finished through 2015. Electric Nation, which was 2016 through to 2019, and then 2023 is when we started the project we're currently in the middle of delivering right now, and that's due to finish in late 2026. So I won't run through all the details on the slides because we'll touch on to the key points in the upcoming slides coming through. But what's important to note is that as these projects progressed, the complexity of the systems that we've used in order to run these trials has increased. The volume and range and complexity of the electric vehicles have actually increased over that as well, and just the sheer numbers of vehicles that are on the network, and hence customers available to participate in these trials, and the willingness of the population in general to start to use electric vehicles. So, My Electric Avenue. So back in 2012, when we first pitched the idea of My Electric Avenue, the full extent of how EVs would disrupt or benefit the distribution network wasn't particularly well understood. We could look at it from an engineering perspective and identify there is likely to be some issues, but there was simply no data to allow us to actually quantify that. At that point, the only mainstream electric vehicle there was the Mark 1 Nissan Leaf. So that had a 24 kilowatt hour battery, 3.5 kilowatt hour charging was standard with an optional upgrade to 7 kilowatts. Whereas now, pretty well all vehicles will have a 7 kilowatt standard, and the capacities for the batteries start usually at about 60 odd kilowatt hours, typically between 70 and 100. It's quite common to be able to buy ones at double that if you particularly wanted a range extended version. So the simple dynamics of how these different electric vehicles are going to impact the network have significantly changed just over the last decade. Now, networks designed using a level of variability or diversity, and it was clear that electric vehicles were going to, as they became more and more mainstream, that was going to change what we call the ADMD expectations for properties. So the average diversity maximum demand calculations was going to shift, but we didn't know by how much. So MEA was pitched and then awarded to determine how disruptive the electric vehicles would actually be to the network load, to test a truly prototype first generation, and by that I mean incredibly basic, it worked, but very prototype first generation method for managing EV loads to protect the network, and then gauge the acceptability of smart charging with customers to determine, is this something that's actually viable and it's worth the networks investing more in. So visualizing what My Electric Avenue found regarding charging behaviors perfectly demonstrates the need for smart charging. So a typical domestic diversified demand curve looks like the blue line on the top left plot. But what we found is when we analysed all the data from over a year's worth of our uncontrolled charging participants, we have this charging profile. So this is additional EV load that's being applied on top of normal domestic property load. So I will caveat first that at these points, there weren't any commonly available time of use tariffs, which are now pretty common now in the UK for people to be shifting. And of our trial participants on here, very, very few were on the Economy 7 one. They simply just weren't the sort of typical people who would do it. And back then, the cost of electricity was so cheap that actually, relative to the cost per mile of the petrol vehicle, people simply didn't bother changing to Economy 7 because it was only a marginal saving on top of what they were already saving by moving. So this curve is also, as a reminder, using the lower capacity charging rates and the lower capacity batteries. So it's an early days system from over a decade ago. But that being said, in the UK, the average car is only driven about 18 miles a day. So the energy requirements is not going to have significantly changed from then to what we're looking at now for the average vehicle. But even so, when we combine those two curves, what we see is a significant increase to this diversified profile, more than doubles the evening peak loading, and demonstrates quite clearly why there is a need for this level of smart charging, because that is introducing additional risks to the network operator, from voltage issues to asset overloading, increasing strain on protection systems. Now, within MEA, we used a local charging management system which just simply had a basic relay which we could remotely control. So we had a monitoring system in the substation, monitoring each feeder and each phase in real time. And then it was using Powerline Carrier to communicate with devices hooked into the charging points in individuals' properties. That allowed the system on a simple level to, when it identified that the loading was increasing to above a point that we'd set, it could then turn off selectively individual charging points and help balance the load. Now, PLC didn't work wonderfully. It was a really good idea in terms of the fact that it solved the fact that there was fairly dodgy comms in terms of mobile communications in a lot of the areas, but it wasn't an ideal system overall. But it did help with this overall system. It proved the concept of what was required for smart charging. And it also allowed us to test it and see how customers would react, which was the key bit. Because what we found is that the charging load clearly adds to the additional evening peak demand. And the increases to EV specifications since then, when we look back, will not have reduced that problem. If anything, they'll have made it worse, but it won't have reduced it. The increase in ADMD it went from around 1 hours, again, noting that was with 3.5 kilowatt chargers. But the recent specification improvements has likely increased loading potential if people are now able to be doing greater journeys and charging faster. Modeling all of the data we pulled from all of this suggested that by the time we have widespread, and by that we're assuming around 40 million plug-in vehicles on the networks in the UK by 2050, the adoption of EVs across that level is going to require at least 30% of the low voltage networks to have been reinforced. And I also was noting at that point, we weren't at that level including consideration for things like electric heat pumps and so on onto networks as well. So this was just 30% of network requiring reinforcement just to accommodate the EVs. So we found that basic load control of EV charging was technically feasible. PLC was unreliable in some instances, as I said. Didn't like cable joints. It was not happy going through that. Participants, however, did accept demand of their management of the EV charging, which was something which was strongly suspected wouldn't be the case by other people elsewhere in the industry. But what we found is participants were quite happy so long as they had their charge by usually about 8 o'clock in the morning for when they were likely to need it the next day. They didn't care what we did to the charging within that time period. Overall, the learning from all of this fed into other projects, which Esther's going to touch on in a moment, but it also contributed to the UK government's decision to mandate smart charging capability to be required in all new domestic charging points. So there was direct data which fed into that, so helped feed through to help prepare for solving and preventing the problem getting worse. So Esther for Electric Nation.
Thanks, Tim. Good morning, good afternoon, everyone. So I'm going to talk through another couple of projects from the UK, and the first one of these is Electric Nation. So as we had on the timeline, we did this a year or so after the conclusion of My Electric Avenue. And this was around kind of taking what MEA approved in terms of, okay, electric vehicles really are an issue, but flexibility looks like it's has got potential, and expanding that understanding. So between the start of MEA and this project, we were looking at a much greater range of vehicles being available, and 7 kilowatt charging was becoming the standard. If you had a full battery vehicle, most of them were charging at 7 kilowatts. And again, looking at the technical feasibility and customer acceptance of smart charging solutions. And in this case, it was smart charging done by interacting with the charge point. That slide's just come backwards. So we delivered this for National Grid Electricity Distribution, who at the time were Western Power Distribution. Okay, next slide, please, Tim. So this slide gives you an overview of kind of who was involved in Electric Nation and some of the data that we received. So much bigger than MEA in this, we had 673 participants, and they were spread all across NGED's 4 license areas. You can see them with the red dots on the map. And we didn't place any restriction on what type of plug-in vehicle people had to take part in this trial. So we had the full range of vehicles that were available at the time. So plug-in hybrids, some range extenders, which were almost exclusively BMW i3s, and nearly 50% were battery-only vehicles. Now, we're saying at this point, actually, battery-only vehicles and larger battery sizes were slightly overrepresented compared to what was being sold at the time, but more typical of actually what's being sold now. And the breakdown of that in terms of battery capacities in the trial is shown on the bar graph. This trial ran for 2 years, had 4 stages, which I'll talk about on the next slide. But over that 2 years, we collected data from over 130,000 charging events. And what that gives us is the ability to kind of really get into some quite detailed learning about charging behavior, and kind of enough data and enough participants to be able to break that down and say, well, if you've got a bigger battery, what does that do to, say, charging frequency? So there's quite a lot of data available on this one. In this project, we had 2 providers of smart charging, essentially given the same role, but their systems work slightly differently. I'll touch on that later on. Okay, next slide, please, Tim. And this trial had 4 stages in it, and the table kind of takes you through those. So at the baseline stage, smart charging wasn't active. That was just about collecting data on how people are charging, and also kind of as we brought on more and more people into the trial, our numbers grew until we eventually had everyone in. So at that stage, no smart charging active, so there wasn't any need for participants to interact with that system, and they weren't being paid any incentives by us that were linked to what time of day they charged. So that was purely just kind of get on with it and we'll collect the data. Trial 1 we call blind, because at that stage we turned on the smart charging algorithms, and I'll talk about how that worked later. But the participant was kind of divorced from that. So the smart charging system did what it was going to do, but the participants couldn't then interact with that and say, no, I'd like to override, or I've got this journey. That sort of interaction wasn't available. And again, no incentives from their charging behavior. Second trial, we gave them apps, essentially, so they could now either press a button that said, I would like high priority, so for this particular charging session, override smart charging, or they had a journey planner. So essentially they could express their need for charging, and then the system would use that information to prioritize. And in the final stage, they still had that app, but now we introduced a time of use reward, which essentially penalised them if they charged in the peak period and increased their reward if they charged outside of that. So we were kind of encouraging people with tariffs, and we'll talk through the results of that one as well. Next slide, please. So as I said before, we had 2 providers of smart charging in this project, Greenflux and CrowdCharge. essentially given the same role, but the customer interfaces they provided were different, and they were using more or less the same comms method. So big change from MEA to this project is that this was controlled via OCPP 1.6, but it was the very early days of OCPP 1.6, which introduced smart charging functionality. And at that stage, not all implementations were equal, I think it was fair to say. So for the purposes of this project, Greenflux essentially said, we know our systems integrate with this charge point. CrowdCharge said, we know ours work with this one. So everybody in the trial got the same charge point depending on which provider we were linking them up to, which worked for this project. But clearly from an interoperability point of view, this isn't how the world works. We need a system long term where regardless of the make of vehicle you've got or the make of charge point you've got, you're able to provide flexibility services. And in this project, we kind of took on the role of DNO, and we were issuing profiles to the management providers that said, this is the amount of available capacity you've got. So we took historical loading data, compared that to a scaled down asset rating and said, okay, the difference between base demand and capacity is this. So your EV load needs to fit in a gap. And if at any point it looks like load is going to be greater than that gap, then implement smart charging, turn that down, prevent it going over capacity. So we were issuing those profiles. We're saying in this project, those were static. So they had a weekday and a weekend, and it wasn't a live link. We sent those to management providers. They sent signals out via OCPP to chargers, and then the chargers sent data back to them to allow that smart charging system to work and also to collect a bunch of data so we could analyze things like charging behavior. Next slide, please. I'll talk through some of the kind of three key findings from this project next. So the first one is around understanding, well, what does load look like? What does that do to networks, and can we do something about it? So I said before that basically whenever, if it wasn't managed, the extra load from charging was going to exceed the difference between base load and rating, then smart charging kicks in. And kick in it did. Most winter evenings in the evening peak, we were regularly having smart charging active. And what that tells us is that if we don't have smart charging, then available network capacity would have been exceeded, which is what we expected from My Electric Avenue, but we proved it here. And it was widespread to the point that in the first trial phase, over 75% of participants had at least one of their charging events were managed. You might look at that and go, well, what about the other 25%? And the answer is that some people on this trial were on a time of use tariff or had decided just because they preferred it that way, they would set a timer and the car always charged in the middle of the night, in which case management wasn't touching because we only managed generally in evening peak. And the second part of this is about, okay, so we know we need to do some smart charging. And then we looked at, well, how flexible is charging load? And the way we did that was for each charging event, we knew how long the charging took, and we know how long the car is plugged in for. So we used those numbers to come up with a flexibility metric. And what that's essentially saying is that if you've got a charging event where it's charging for the full time it's plugged in, and you reduce the speed it charges at, then when the driver comes to unplug, then they're going, well, the car should be full, and it's not. And the answer is because you slow down the charging. However, if, as is actually the case, people plug in the evening, they leave it plugged in for 12 hours, it actually only needs to charge for 3, and you slow it down, it's caught up by the time by the time it's unplugged in the morning. So you can do the thing that Tim said where actually people don't notice. And so we calculated this flexibility metric for all the charging events. And if we go on to the next slide, then we can see what that looks like. And this is showing the distribution of flexibility depending on the time of day when people plug in. And the takeaway from this is that flexibility is really pretty high, and it reaches its peak just when we'd like it to in the evenings. That's shown by the green box. What you're seeing on here is essentially a distribution of flexibility. So you can see that means that in the evening peak, then around half of charging events have got a flexibility of about 80%. So you can really slow these down without having any impact at all on state of charge when people unplug. And this is good news because flexibility in the evening peak is exactly what we're looking for. Next slide, please. So we wanted to understand, okay, technically from a can you send signals, do chargers respond, does this work? Yes, it does. We kind of prove that. And also we think based on flexibility, people are going to accept this, but will they really? And the way we understood that was by taking regular surveys of our participants. So in each stage of the trial, they were asked, how satisfied are you with your charging arrangements on a 1 to 10 scale? And the results from that are on the graph on the slide. And what you can see there is that satisfaction remained really high throughout. So over 80% saying, yeah, highly satisfied, 8 to 10 score. And we didn't get any statistically significant changes in that level of satisfaction throughout the trial. So even the point where we were managing them, they couldn't interact with that system, they were still highly satisfied. The other piece of analysis we did was for each participant, we knew what their experience had been. So was this somebody whose charging we were controlling every single night, or was this somebody we never touched? And we looked at those groups and their levels of satisfaction. And what that showed us is that there is actually no link between how much you curtail somebody and how satisfied they are, which is a really good sign in terms of EV flexibility going forwards. Next slide. And the final bit I'll talk about for this project is around trial 3, so time of use plans. And what we did in this period was essentially give people, they all started off with £10 as a reward value, and depending on what time of day they charged, that number would either go up or it would go down. So if they charged in the red period, so over the evening peak, then the reward went down. And if they charged anywhere outside a red bit, then the reward value is going up. And the system that Greenflux implemented meant in the app they could select a charging preference, and what that effectively did was control what time of day charging will be active and supported people to change their behaviour. So it made it really easy. They could just select a setting once in the app and it would apply until they changed it. And broadly, the two that people used most were either optimize time, i.e. don't care about this tariff, just when I plug in, charge immediately, or minimize cost. And what that meant was that if they had plugged in before 4:30 in the afternoon or during that window, charging would be paused and it would start again when the very off-peak period started at 10 o'clock at night. But they didn't have to do anything. They could just plug in as normal. The app managed it all for them. And I say that setting then applied until they changed it. So next slide, please. And this is going to show, as we click through, quite what a difference this made. And headline finding, it's very effective. So starting off with just the graph then, you can see what this is doing is comparing our winter loading 90th percentile for trial 1 in the grey curve, and then what we got in trial 3, which is the blue. And there are 3 things to look at here. So Tim, you can click the first time, we'll look at the first one. And the first kind of headline takeaway from that is look at what happened to the evening peak. So you can see a big reduction there between evening peak demand between the grey curve and the blue. And this was so effective that actually smart charging was never active during trial 3. This change, this incentive and smart charging alongside it meant there was always enough capacity available for the people who did want to charge in the evening peak. And the next point. You're going to look at 10 o'clock and probably go, well, what happened there? And the answer is that all of the charging events, in the way this was implemented, all the charging events that had been paused started at the same time. Now, clearly, from an energy system point of view, that is not desirable. However, when you've got smart charging, you can change that. You can randomize the start time, you can extend it out, you can do something that distributes when charging starts. If you have a tariff incentive and people just use a timer in the car, there is nothing to stop everybody going, well, my off-peak rate starts at midnight. They all program midnight in and you get that kind of peak. And it's one of the things we'll look at in the trial that we're doing at the moment. So yes, we created that peak, but we also could have managed it. We just didn't in this particular project. And the final one, you can see kind of where this demand that we didn't supply in the evening peak happened. So you've got the blue line higher than the grey through the sort of start of the night and the early hours in the morning. But by about 3:30, we'd caught up. So you can see there that actually we have still got the potential to randomise the start time, move some of this peak demand out of the 10 o'clock period, and still catch ourselves up by the time everyone unplugs their vehicles at sort of 7, 8 a.m. Okay, next slide, please. And this just gives us some findings in terms of what participants thought about this bit of the trial. They used the app quite a lot, 60% of them used it at least once. Nearly half of the events were set on a setting that said, don't charge in peak times. And one of the concerns that people have had around time of use tariffs and EV flexibility is, oh, will people understand this? Are they going to be happy with it? And our survey said, well, yes, they do actually. So 86%, when asked, did you understand the reward structure? Was that easy to understand? Said, yeah, very easy or easy to understand. They said they'd be likely to do it again in the future, which is positive. And over 3/4 of them would recommend that kind of setup to a friend. Next slide, please. So we're now on to our current project, and what we're looking at here is the Northern Ireland Intelligent EV Charging Pilot, NEVE, and we're delivering this currently for Northern Ireland Electricity Networks. What this is wanting to do is that NIE can see the uptake of EVs coming on their network, and what they want come the end of this project is an EV flexibility service that is ready to go, that can be their business as usual EV flexibility offering. So this project is about kind of developing that system, understanding how it works and refining it. And also understanding charging behaviour in Northern Ireland, customer appetite and ability to participate in EV flexibility services. The other thing this will give us is kind of understanding of charging behaviour post-COVID, when we think working and driving patterns and commuting patterns have changed, and post-energy crisis, where customers are a lot more sensitive to price. And as a trial, we are in the baselining period at the moment. We just started that a couple of weeks ago, and this is running for a 20-month trial. We're looking at about 350 to 400 participants. We're just getting everyone onboarded kind of as we speak. Next slide, please. In this project, EV flexibility services are being provided by ev.energy, and the big difference here, as you can tell from the bottom of the slide, is that they can talk to a much wider range of vehicles and charge points. So some of that is going through vehicle telematics and vehicle like OEM systems. Some of it is OCPP to charge points. So we're moving forward in interoperability. MEA, no smart charging, extra relay installed. Electric Nation, no, use this very, very specific charge point. We know it works. This one, much wider range, but it's not fixed. We were still having participants who couldn't take part in this trial because they didn't have the right hardware. And that going forward is not something we would want. You need to have the kind of largest pool of potential participants, and that is an interoperability challenge. ev.energy then are sending those control signals back and forth to cars and chargers and getting usage data back from them. And the control in this one is much more complex. So we're taking LV monitoring data on a real-time basis, using that to forecast a day ahead what we think the demand is going to be, and then sending turn down signals, or this is the predicted amount of capacity you've got, on a day ahead basis via API. So much more complex, much closer to real-time control than we did previously. Next slide, please. And the trial design for this, 4 phases, currently in baselining. So this is understanding what the existing behavior looks like in the absence of smart charging. And then we're doing kind of 2 flavors of flexibility. So trial 1 is what we're calling DNO led. So this is about DNO monitoring load versus their network capacity and sending those signals based on that network loading. In the second trial, we're moving towards a more supplier-led model. So if we have innovative plans and tariffs and we combine those with smart charging, what difference is that going to make? Are we actually going to find that a supplier-led flexibility proposition with smart charging means that the DNO's need to call for flexibility is much lower because demand has already switched into periods where there is enough capacity available? And the final stage in the trial will develop as we're moving through and getting the learnings from the trial. But the idea there is essentially we hone in on what is going to be the business as usual implementation, and we trial that for 3 months. And that will come out of the learning, and it'll come out of how systems develop over the next year or so. We're incentivizing people to take part in this trial. They already have to have their home charge point, but they're getting paid to sign up. We're offering £5 a month, which we've tried to set to be reflective of actually what could be available business as usual. And then there's incentives around completing surveys as well. I'll pass back to you, Gendro, to talk through some solutions for Australia and New Zealand.
Thanks, Esther. So I'll actually very quickly present just 2 case studies, which are related to the EV flexibility. So next slide, please. The one is just to demonstrate that, we did work for an Australian DNSP where EV was considered as an issue for the network management. And then EA technology has the capacity to actually build the network, even when there is no network connectivity, to build the network from the data using the parametric model, and then test the different LV management strategies and say which one will be best using the network options and non-network options both. So in this case, what I'm trying to demonstrate is if you just focus on one scenario, like a step change in the middle, we tested like 2 mechanisms to manage this charging. One is by tariff, which is time of use tariff. And the another one was demand side participation, which we can call it as flexibility, in terms of demand response. And this shows that, there will be overall, savings in terms of deferring the augmentation work for that particular, network size. There will be, network savings. If people just use the baseline time of use tariff. Baseline time of use tariff there was an assumption, let's say 30-35%, opt in for those kind of tariffs. And then if the more people, opt in, medium thing, the savings increases, more people are time of use tariff. That means, the peak demand is managed, and potentially in future, the minimum demand is also managed using the same thing. But you will notice that, like, when there is a high TRU, the savings reduces, and it is very obvious, because the high TRU means that it will create another peak, and so that is the why you see some reduction there. And other 3 bar lines, they actually talk about the demand side management, under these scenarios. Low participation from demand side, medium participation, and high demand side. It's not changing much here in this case. Just wanted to let you know, that just because the network constraints were like that, they were easily met by certain percentage of demand side participation. Just wanted to let you know that how EV flexibility can then be used to actually decide which LV management strategy it will be optimum right from now to 2050. And that's the kind of job, just next slide, please. This is another thing which, we were, Tim and Esther was talking, interoperability. So that means that we need the standards. How the flexibility service providers or aggregators, how they are going to talk to each other, how they are going to talk to customer, and how they are going to talk to the different models of charges. Some dumb chargers, some not dumb, but dumb they can't talk, but semi-dumb there are there, and there are very smart chargers. How they are going to talk to that, and then there is another level of command from between the EV charger to the car. So all these communication protocols, how many will be used as APIs will be used, and how many, like the open communication protocol will be useful. So this is a kind of a study we actually did for EEA New Zealand recently, and we said what is the best open communication standard at the moment. There were two candidates, OpenADR 2.0, of course 3.0 is also nearly there, and IEEE 2030.5, and seeing they have their own strengths and weaknesses. This is available. This work is available on EEA website, and we also actually so how UK DNOs are actually managing the flexibility using the commercial flexibility providers, and generally it is using the API, which is an indication that APIs are early, science of managing that thing, unless a broader open communication protocol is developed, and ultimately all these APIs will lead to another protocol. So next one, please. Next, yeah. So just to summarize, what we are talking here, the next slide, please. We have seen that for CR coordination, the blue bit I was talking in the bit, to have that effectively, we need to understand the network capacity, the hosting capacity, the visibility of that. The CERs has to be active in a controllable. The interoperability definitely required, open communication protocols required, cybersecurity required, customer choices, like how they are incentivized, what is the equity, privacy of things. These are the things which are mandatory to make this any flexibility for CER, including EVs. Next one, please. I'll not go into detail, but what I'm saying is that this is something which Australian National CER Roadmap at a very high level. And it talks of the same things, it's saying the first thing is interoperability standards developed. Another thing is it also talks about, with the green car sign, is that identify options for harmonized CER connection processes. And another one which I highlighted with the red thing is removal of barriers to enable vehicle to grid kind of things. And then another one is talking of CER cybersecurity, and then it is also talking of secure communication systems, where including the customer privacy and data privacy. So that means all these things which we have been talking are on the roadmap, and they have to be developed to take full advantage of the flexibility. I now hand over to David to conduct the Q&A session.
Thank you, and thanks everyone for the presentations. Interesting talk through there over the 10 plus years that we've been studying electric vehicle charging, and some of the changes in technology and changes in vehicles over that time, and how it's each trial builds on learning from the previous ones. We have got a couple of questions just to kick us off a little bit. So I'm going to ask this to you, Tim. You talked about sort of diversity and ADMD and demand profiles. And then obviously Esther put the indication up there around the peaking as a result of time of use tariffs. Are you seeing any challenges around how we might calculate diversity and demand going forward as more and more customers sort of shift into this?
Yeah, it's one of the things we're looking at to try and work out the best way of dealing with it within the Neve project at the moment. It comes down in a lot of instances to just the data is there, the information is available. The problem is getting the right information into the right place for the right companies to be able to make use of it. The way the UK and sort of GB networks generally set up is we have very strong data protection laws for consumers and everything else related around that, but the DNOs have quite rightly a lot of nervousness about publishing too much information about their networks. So the networks can monitor and know exactly what is going on their networks to a very high degree of accuracy, but they don't know what proportion of the load they're seeing is actually from EV. They just know there's a total load. The problem is the other end, like EV.energy in this instance, know exactly what's going on with each of their charging participants because they're monitoring their charging, but they don't know how much energy is being provided through the network as a whole, and they can't share all of that information on an individual basis to the DNOs because of the data protection laws. So one of the things that we need to be exploring and working on within the Neve job is to try and work out what is the optimum way of combining all of that data in a way that doesn't breach data protection, doesn't put too much information out regarding the network that would be sensitive, and allows the right level of understanding to be in place so you can do the control and take into account the individual time of use preferences, time of use tariffs, and what's going on the network. So yeah, it's a challenge. It's solvable around the data. We can see solutions to it, but they require commercial sensitivities and agreements as well, which is where a lot of the conversations sit at the moment.
Great, thanks. And so, yeah, in the future, maybe able to improve understanding of when demand will move around and how that might impact diversity. So, Esther, there's a question around effectively the difference between some of the challenges around the national level and demand matching, and then the local level. I wonder if you could just elaborate a little bit on how the projects are looking at tackling that. I think Neve particularly sort of looks at some of those challenges.
Yeah, so the control system in Neve, as kind of we've built up this complexity, works on a hierarchy. So at a kind of the first level of that is we must respect the user's time of use window. So if they've got an off-peak window, then charging can't be shifted outside of that. And then it says, okay, well, now also optimize for the DNO signal. And then once you've done that, we'll optimize for carbon. The question in the chat around, can you look at the loading of the building, essentially becomes another input to that hierarchy that says another thing that we must satisfy is essentially you could have, I'm thinking about our office building, we have a bank of 10 chargers, I think, at the front of there. We could say the capacity we have in this building for this group of chargers is X kilowatt. And that becomes a group limit that works the same as the network capacity. It's just on a much more local level. So the same types of control can be used. It just depends kind of how you group your chargers. Do you do it they're in a building, or they're all from the same LV feeder, or they're all on the same primary substation? Same philosophy, just different numbers.
And that obviously all taking account for any, or so in the UK, there's work going on to understand the avoiding conflict between, say, our ESO instructions or through our suppliers and the local network challenges, and understanding who has priority when there's a certain dispatch and that sort of activity as well.
Yes, so kind of building those rules into that control hierarchy that essentially says who wins, because from at the extreme level, if you have blown the feeder on the blown the fuse at the LV feeder, then optimizing time of use tariff kind of goes out the window if you've got a power cut. So it's about kind of where you set those limits and kind of working out those conflicts.
Thank you. And so Ugendra, obviously, we've done lots of trials in the UK and some of the work presented here. And just wondered if you had any view from Australia and kind of how the role of EV flexibility is evolving in obviously a slightly different market with different vehicles, different standards of typical driving ranges and those characteristics.
Yeah, I mean, look, in terms of the EV uptake, is definitely happening. The only difference was the kilometers generally driven, and that was initial thing in Australia because the land size. But that has been largely, addressed because of every car is now more than 60 kilowatt hours. So that means every car, which I saw last time, there was 70 models available in Australia. Everyone has more than 400 kilometer range. So I think that thing, which was very peculiar and which might be holding a little bit. So there are two things. One is the range, and the second one is the charging infrastructure, which is also, progressing very well. So in terms of uptake of EV, there are no barriers. In terms of the economics and the government policies to incentivize, it is coming up. So it all depends. This is where I mentioned the national EV policy, strategy, because that there are a lot of issues where, how this is all promoted, against the fossil fuels, and that policy is still taking shape. That government policy incentives to allow the uptake is happening. And then there are a lot of trials. In fact, what Esther was saying, that there have been a lot of trials how this optimization engine will work ultimately for who will optimize for whom. So connection is so like if you see the charter, it says that it has to be done for the customer. Ultimately, the customer benefits. So customer is at the center, and so we are optimizing for the customer. But as long as the network can work, as long as the bulk power system can sustain and work securely. So to that effect, there's a lot of trials which are saying how the marketplace will be there, how the standards will be there, and how this optimization will happen, which will actually give the best value. And there will be equity, in that. So there's a lot of work happening in this part of the world.
Good. Looking forward to lots more findings coming out from that and seeing how it can help inform the future projects and trials that we look to. Well, I'd say from my side, thank you to all the presenters, and thank you for everyone who's joined to watch us this evening or morning or wherever the time is for you. I hope you enjoy the rest of your day. I think that's the end of our
Thank you all, and special thanks to the UK team who had joined early morning. Thank you.